Thank the organizers for the invitation to speak in the school. It's really a great pleasure to be here. It's my second time, and I'm very pleased every time I visit this place. So, since my abstract was very brief, please let me start with the plan of the lectures. So, first I plan to speak about Syzygies. What are Syzygies, and how do we compute Syzygies? Then I will speak about Syzygies of KAIST, mostly vanishing, non-vanishing. Then the fourth part will be about Lazarsfeld Mukai bundles and their role in Voisin's proof of Green's conjecture for generic curves. Which is at the moment the only correct proof for Green's conjecture, for generic Green's conjecture. And if time allows, I will just briefly address the subject of Ulrich bundles, which has been studied for many years by algebraists and has recently re-emerged in algebraic geometry in relation with the Boy-Söderberg theory. So for the moment, let's speak about Syzygies. And let me start with the motivating question. So suppose we are given x in Pn, a smooth projective curve. By the way, I should mention that everything happens over a field, algebraically closed field of characteristic 0, although many statements are true also in positive characteristics, but Green's conjecture, for instance, fails in characteristic P. And the question is, since we are interested in projective geometry, the question is, why does X require cubics in the ideal? So this is V, is the span of the variables. So why this map is not surjective? So there are several possible answers. So the first obvious answer is the following. Sorry? Yeah, thank you. So the first possible answer is related to this embedding. For example, if there are trisecant lines, if there is a trisecant line, then we necessarily must have cubics in the ideal that do not come from quadrics, as any quadric should vanishing on the curve will vanish on the line as well. But there are also other answers which
actually, what you say is not completely correct, or you must put some assumptions. You mean that it's not that I2 tensor SMV to I n plus 2 is not subjective to all n.
Yeah, sure,
Essentially that.
Yeah, essentially that. So, and this introductory part, I'm very imprecise. Okay, thank you. So the second possible answer concerns the intrinsic geometry of the curve. So, spatial geometry of the curve can be one reason for existence of cubics. For example, if we take genus at least 4 and X is embedded in Pn by a line bundle of degree 2g plus 1, which is general. So then this embedding doesn't have trisecant lines. However, if the curve X is hyperelliptic, then the ideal is not generated by quadrics. And the reason for that is that if the curve is hyperelliptic, then X is embedded in a surface of minimal degree, and surfaces of minimal degree, so in particular the quadrics in the ideal of the surface are among the quadrics in the ideal of X, and surfaces of minimal degree have many relations. So quadrics in the ideal of a surface of minimal degree have many relations. Linear relations, I should say. So at least there are many linear relations than expected from the Hilbert function. And this implies the existence of cubics. So in general, this is the kind of questions that the Syzygy theory tries to address. So the question is, what are the relations, if any, between Syzygies, which I haven't defined yet, and the geometry. And I hope to convince you that there are interesting things happening here. Okay, so let's define Syzygies. So the setup for defining the general setup is the following. So let's consider V vector space over K of dimension, say, n plus 1. We take S to be the symmetric algebra of V. And we consider M a graded, finitely generated, graded S module. And then by the Hilbert-Syzygy theorem, I think it's 1890. There exists a minimal free resolution of M, which is of finite length. Up to some point. Graded, yes. Where so FIs are graded free S modules. And the minimality means the following. So since these are graded free modules, all these maps can be seen as given by some matrices with entries homogeneous polynomials. So minimality means that among all the elements of these matrices there are no non-zero entries which are constant polynomials. Or in other words, if we mod out the irrelevant ideal, so if M is the irrelevant ideal, and we twist by S over M, then all the maps vanish.
Twist, you mean the tensor?
Yeah, tensor. Yeah, over S. So Hilbert's great idea was, why did he? So he was aware at that time, although the notion of a module was not clear, that once you try to do linear algebra with.
To say that R is smaller than n plus 1.
Yes. Yeah. Thank you. When you try to do linear algebra with variable coefficients, then the space of solutions of some linear system is not necessarily free anymore. And he tried to approximate. So we can. The best way to see this minimal resolution is like an approximation of a module by free modules, and we are forced to go all the way to the end, just to have a complete picture of.
So you still haven't said what syzygies are?
No, I'm I would say right now. So a syzygy is a relation in the free resolution above. And these syzygies are characterized by I should mention that this not only that free
You mean it's the image of one element in some Fi?
Yeah, exactly, or an element in the kernel, if you put it as a relation, is in a is the same, of course.
Marian, look, say F naught are the generators of M.
Yes, I'm going to say. Exactly. I was going to say that. Yes. So right, so F naught, actually every Fi can be written as a direct sum minus I minus j, Kij over all j, and in many other references you will find a different notation. The summation is taken over as j, and here you have beta ij, the relation of course being Kij is eta I plus j. And what are the meanings of these numbers? So these are called graded Betti numbers of M. So what's the meaning of these? So F, as Miles mentioned, so F naught will give the generators. Actually, not only because of minimality, gives a minimal system of generators of M. And this K0 J give the degrees of the generators. So, for instance, if the ideal of a projective variety is generated by quadratics, this would mean that we would the first F naught would be a number of copies of S of minus 2. And if...
So that's where M is I of x.
Sorry?
That's where M is I of x.
Yes, yeah, exactly. And then the next one, F1, so in F1 we read the generators of the relations between the generators of M. So these are not independent.
So just to agree, these are the first syzygies.
These are the first syzygies, exactly.
Really?
So they are the first syzygies. And then in F2, we read the relations between relations. So these are the second syzygies, and so on. So then we get higher syzygies in in Fi. Let me give you an example, a very short example. So if X is in P3 is a twisted cubic, then the generators of the ideal are the quadratics given by the 2 by 2 minors of the matrix X3. So the 2 by 2 minors give the generators of the ideal. And what are the relations? Well, there are two obvious relations. If we copy any of the two rows and we make a 3 by 3 matrix, then the determinant will be 0. And they are really linear relations. And actually they span the whole module of relations. One can prove that. So they are precisely two linear relations. And hence the minimal resolution of the ideal is the following: I of x s of minus 2 to the cube, and then we have s of minus 3 to the 2. So the difference between these degrees are the degrees of the generators.
You transpose the matrix.
Yeah, we transpose the matrix. Okay.
Look, it's really useful to say the syzygy is, if you take that matrix and write down it with one repeated row,
Yes.
the determinant is identically 0.
Yes.
And the determinant is also that linear combination of the minor.
Yeah. Yes. Yeah. Yes. And just to keep track of all these numbers that appear here, we organize them in a table which is called the Betty table. So I should take the so there are two conventions. Either we start from the right side to the left, or from the left to the right, depending on whether you are a Macaulay fan or not. So, sorry?
You took going to the right, and Macaulay goes to the left.
Yeah, it's exactly the reverse for Macaulay. Yes. But I don't use Macaulay so much. So, we start from, say, from 0, 1, and so on. And here we increase. So we increase from the right to the left, and from up to down. And here we put these numbers, K, J. This is ith column and jth row. Sorry. So, for example, if we consider the homogeneous coordinate ring of
But you call it betas are Betty numbers, but now the Betty table is not with the Betty numbers.
yes, it is with the Betty numbers. So it's
The matrix is K and J. So
this is beta I plus j.
no.
So this is the convention.
Look, we make the convention that the table is skewed by that j.
Yeah, that's correct.
And the reason
I'm
is
just saying, why didn't
you're
people call the Betty
expecting
numbers
all the
K and
syzygies
J?
to be linear.
Yeah, this is the explanation. Why do we take this convention and not organize as beta ij as usual? Because on the horizontal, sorry?
The betas are bad.
No, they're not bad. Why? Why do you say so?
Why do you put the K? So you think they're better.
Well, I have a reason, because I'll speak about Cazul cohomology. So these are dimensions of Cazul cohomology groups. So the reason is that if you go on a horizontal row, then the horizontal row you read actually linear syzygies. So on horizontal directions, you read linear syzygies. And as Miles mentioned, in many cases we expect this table to be as linear as possible. So if we use the other convention, then the shape would be much funnier than this one. And another explanation is regularity. So the number of rows is the regularity. So otherwise, if we took the other convention, we would have regularity would not be read in the number of rows, but in some diagonal. Okay. So let me just give this example. So if x
horizontal directions, you read linear syzygies. It's a little bit vague.
yeah, it is vague.
I don't understand it.
Yeah, I will explain in this.
Why not?
So if you take a non-degenerate variety in a projective space, let's see what is this the Betty table of this module. So
S of x is S mod I of x.
right. So we always start with the 1 here, because this is generated by S, and then after that we don't have any linear so this is non-degenerate. We don't have any elements on this row. Why? Because being non-degenerate, we have nothing in here, in this position. Actually, on this column, we read the generators of the ideal, I of x. So that would correspond to hyperplanes in the ideal. Here we would have quadrics in the ideal. Here we would have cubics. So in this notation, that would be beta 1, 2, beta 1, 3, and so on. Quartics. So in the first column, we read the generators of the ideal. Then let's pass to the next column. So here we have the relations.
Beta, that's 0. There are no linear relations if it's non-degenerate.
That's what you say.
Yeah, but you didn't write it.
But you wrote.
You write dash instead of...
Yeah, I write dashes instead of zeros. Yes. So now come the relations. So here we have, so as I mentioned, so on this strand we read the linear relations. So here we would have all the linear relations between the quadrics in the ideal. Like in this case, when we have two linear relations that span all the relations because of the reason that Miles mentioned. And here we would read linear relations among cubics and quadric relations among quadrics. So let me give you another example. So if we take x in P3, an elliptic normal curve. So this is complete intersection of two quadrics. And so this is, so the ideal is generated by Q1 and Q2. And these quadrics do not have linear relations, but they do have one quadratic relation, which is the following: Q1, Q2 minus Q2. Q1 is 0. This seems to be a bit silly, but it is not. I mean, although it's a trivial mathematical fact, it's a non-trivial. It gives a non-trivial relation in this Betty table. So
You must say clearly and loudly, this is the Koszul complex.
yes, yeah, this is a Koszul complex for complete intersections. I will come to that.
Yes.
Yeah. And so the Betty table, it's like, so the Betty table of the homogeneous coordinate ring is, we have always one here in this upper right corner, we have two quadrics in the ideal and one quadratic relation. So there is no linear relation. And so on. So we go on with the. So here we read the first Syzygies are the relations between generators and so on. and then the relations between relations and so on. Okay. So some examples. We have already seen a couple of examples. Actually, these examples. So this example of the twisted cubic generalizes to any rational normal curve in Pn, and this is the Egan-Norcott complex. And this also generalizes to elliptic normal curves in Pn. So there is, for example, the standard textbook of Heisenbad on the geometry of Syzygies, but there is also a paper of Jonathan Wall back in the 70s, 74, I guess. So these are two cases which we understand completely. Now,
the Norcott is essentially a direct image of a constant complex.
Yeah. No. Let me discuss the Koszul complex, because this is somehow the building. This is the building. The Koszul complexes are building blocks for Syzygy theory. So the standard Koszul complex is for the ideal M, the irrelevant ideal, which is generated by variables, and it generalizes for complete intersections in the projective space. So in this case, we take M to be K, the residual field. Then we have the minimal resolution of this graded S module is the following. So we take S over M. Here is generated by S, of course. And now let's write down the other. Probably I should denote by V the span, the linear span of the variables. This is V tensor over K by S of minus 1. This is just the multiplication map. Then we have wedge 2 of V tensor S of minus 2, and so on. It will stop at wedge n plus 1 of V. So V is of dimension n plus 1. Tensor S of minus n minus 1. So what are the maps? So from wedge P of V tensor S of minus P to wedge P minus 1 of V tensor S of minus P plus 1, the map is given by, so X I1 wedge X IP tensor some polynomial is mapped to, I have to decrease the length of this multivector, so I should take out one of them, one of these variables. When I hat, it means that what was here before on position, on ith position, will disappear. XIP. Then I have to put it back. So the only way is to multiply by F. And then I should take the sum over all these j's and alternate.
You're contracting with the sum of xi dual tensor xi.
Yeah, exactly. Yeah, you can see it that way. It's a contraction, yes.
Look, it is much more convincing if you write down the 3 by 3 Syzygy matrix
Yes?
for a codimension 3 computing section.
Yeah.
The skew symmetric image.
Yes, yeah, it's true.
X3 minus X2.
Yes. So this is yeah. So this generalizes for complete intersections just by replacing these variables by the other forms. Anyhow, this is this complex is exact. So we have a minimal free resolution of S over M. I don't know if I mentioned, but free resolutions are unique up to isomorphisms. So when we speak about free resolution, we mean the free minimal resolution. If we don't care about the maps, if we just care about the factors in the resolution. And other cases, so other cases that come from geometry are the following. So if X is a variety, a line bundle on X, V is a space of sections in of global sections, and F, for example, is a coherent sheaf then we try to obtain a minimal resolution of the module direct sum of H naught F tensor LQ seen over the symmetric algebra of V. So this is taken over all Q. This is called R of X, F, and L, I guess. And if F is the trivial sheaf, then we just drop this.
You call it Algebraic module, or?
No, this is for F the canonical. If F is the canonical, then it's Algebraic module.
You should write Q in Z because you want
yeah, sure. Yes, of course. Yeah. It might create some confusion. It's not only natural; it can be all the Q's, right? So the question is how to compute this. These numbers. How to compute the minimal resolution, so how to compute the Betti numbers, the graded Betti numbers of these modules. So we have already one tool here, which is the Koszul complex, and we are going to use it. So the first, so probably I pass now to the second part. So the first way of computing minimal resolutions is by means of Koszul cohomology. And Koszul cohomology is based on the observation that if we look at the back at the minimal resolution, which I haven't erased yet, and we want to compute these Betti numbers, graded Betti numbers. So from the very definition, if we tensor by S over M, then we will cancel all these differentials, which means that right from the definition, this means that these graded Betti numbers, beta ij, are actually the dimensions of Tor over S, I, M, and Sm, the graded piece J. Well, the Tors, since we are in the graded settings, all the Tors are naturally graded. So if we just analyze, we see that this is the case because the differentials vanish. On the other hand, the Tor functors are symmetric, so we can also start with the minimal resolution of S over M, twist by M, and take Tors, take cohomology, sorry, and then we get the same thing. So this is so. In other words, the Kij in the other notation is the dimension of the same thing, I plus j, graded part. So now, so these Tors can be computed from the minimal resolution of the residual field. So what we do here is take this Koszul complex, just remove S over M, twist by M, and take cohomology, and analyze gradings. So if we do that, then we see that these Kij's are the dimensions of the cohomology spaces the following spaces. So we have I here, wedge I V, tensor M J. It looks very much like the usual Koszul complex. So the differentials are, so this is a complex. The cohomology here at the middle will give some spaces whose dimensions are precisely those Kij's. So the definition is exactly like this one, just we have to replace F by elements of M. And everything makes sense because if we multiply by linear form, then we just increase the degree by 1, and then here we decrease the...
Beta ij are this dimension.
No, Kij. We have a shift. You have to be careful with the degrees. So there is a shift, the degrees.
Oh, because you...
Yes, yeah. So this is, these cohomology spaces are denoted by Kij of M or Kij of M and V, just to keep track of the original vector space, because we might make some base changes and then these objects will change as well. So Koszul cohomology is somehow the basic tool for computing graded Betti numbers. And just some notation. In if M is R of X FL, we write Ki J, this is the introduction introduced by Mark Green. X F L V for Kij M and V. And with some sub-cases, if F is trivial, then we write Kij of XLV. If V is the whole space of sections, then we also drop it. And if we are in the intersection of these cases, then we will drop both of them. So we write Kij XL if the two cases are realized. Anyway, these objects are very close to what the examples I have given at the beginning, because R of X and L. So if X is embedded in Pn and L is O of 1, then the homogeneous coordinate ring is embedded in R of XL. And if this is projectively normal, then actually they coincide. Something interesting happens if I is 1. So Ki1, let me just mention this fact. Ki1 of Sx and V is the same as Ki1 of X and L if V is H naught of L, of course. No matter whether this variety is projectively normal or not. So if we just look at the linear strand, then if we are only interested in the linear strand of the minimal resolution, we can take either this module or this module. It's going to give the same thing. And let me now just make one small remark. That actually projective normality can be expressed in terms of Kozul cohomology in the following way. So this remark is simple, but it's quite important. So again, X is embedded by a complete linear system in Pn, and suppose L is very ample. We have already supposed that, sorry. Then X is projectively normal if and only if K0J of X and L is 0 for any J bigger than or equal to 1. So on the if we replace the homogeneous coordinate ring by its integral closure, then a funny thing can happen. So in the Betti table, of K of RXL, we might have, so we have a 1 here, we always have a 1, it starts with a 1, but we might have non-zero components on the zeroth column. So this can happen. For XL, it doesn't happen because it necessarily has 1 generated, but for RXL, this phenomenon can happen, And Kozulka homology keeps track of this pathology, and this observation follows just by remarking that the co-kernel of the multiplication map from V tensor H naught Lj minus 1 to H naught Lj is K naught J of X and L. So co-kernels of multiplication maps are among these Kozulka homology spaces, and then furthermore, the ideal is generated. So furthermore, the ideal is generated by quadrics if and only if K1J of XL is 0 for all J bigger than or equal to 2, because and K11 will indicate the number of quadrics in the ideal. And then if we go one step more, the relations between quadrics are linear if and only if K2J of XL is 0 for any J bigger than or equal to 2. So that inspired Mark Green to give the following definition. We say that L satisfies property NP if Kij of XL is 0 for any I lower than or equal to P, J bigger than or equal to 2, and we should also add K, this K1, K0, and K01 of XL is 0. So that property NP, property N0 means precisely projectively normal. So N0 means projectively normal. Then N1 means projectively normal, and the ideal is generated by quadrics. Then N2 means projectively normal, the ideal is generated by quadrics, and the relations are linear, and so on. So property NP actually means projectively normal and the minimal resolution is linear up to the 5th step.
Just normal idea generated by quadrics.
Yes, and the relations. Yeah, but it's included in the statement. Linear up to the 5th step means that we have the minimal resolution will be beta 1, 2. So this is property N1. There are no cubics or quartics or forms of higher degree. Then beta 2, 3. Then the relations are linear, and so on. This is the 5th step. So they are all 0. So the minimal resolution is very nice up to the pth step. Then it can become complicated. And somehow the expectation is that given a variety property NP should hold unless there are good reasons not to hold. And we try to understand why. So this is one of the goals of the theory, to understand why property NP does not hold. Okay. And just before the end, let me mention now another approach due to Lazarsfeld, which uses kernel bundles. So suppose V generates, V is an H naught of L. L is a line bundle over a variety, X, a smooth variety, say, and suppose that V generates L. Then this will give a morphism to a projective space. If we pull back the Euler sequence from that projective space, we get a sequence. This is MV. This is the kernel of the evaluation map. It's just the pullback of omega 1 of 1 from that projective space. And now if we take wedge powers of this sequence, twist by powers of L, and then take global sections, we get, for example, for some wedge P, we get a sequence like that: wedge P plus 1 of V, tensor L, some Q minus 1, wedge P plus 1 MV, tensor LQ minus 1, and H0. I promised I take global sections, so this is H0, LQ minus 1, and then H0 wedge P MV, tensor LQ. Well, Lazarsfeld proves that if we look at the co-kernel of this map, then this coincides with Kozulko homology. So the result of Lazarsfeld is back in the 80s, is that the co-kernel of wedge of the map, wedge P plus 1 V, tensor H naught LQ minus 1, goes to H naught wedge P and V, tensor L, is isomorphic to Kozulko homology KPQ X LV. And if we look at the other mixed cohomology with a coherent sheaf in between, we should also twist by that coherent sheaf, and we get a similar result for any type of Kozulko homology. So yeah, I will stop here and continue in the afternoon.